This lesson is an overview of the concepts from PBS 3.4.2, What's the Probability? And in this video, I'm going to show you how to use Punnett squares and pedigrees to determine how traits have been inherited or how they might be passed down to children. So first, I have a review on Punnett squares. So in this example, we're going to be looking at sickle cell anemia, which is the big disease for Unit 3. And sickle cell anemia is a recessive trait, which means that you have to have two of the alleles in order to have the disease. So in this case, we have a mother and a father who are both heterozygous. Okay, so hetero meaning different. They're both heterozygous for the disease. So we consider them carriers for sickle cell anemia. So they don't have sickle cell anemia, but they can pass it down to their children, which you will see in this genetic cross. So you're going to put the genotype of one parent on the top and the genotype of the other parent on the left-hand side of your Punnett square. It doesn't matter which one goes where. Okay. And then we are going to cross them. So you see that this box right here represents one possibility of how the alleles will be inherited to by the child. So they give one of these alleles, they give one of these alleles. Okay, so there are three possible genotypes that we can get from having two heterozygous parents. One of them is homozygous dominant. Okay. Homo meaning same, and the capital letter indicates a dominant trait, so this person would be normal for their phenotype. The next one, we have heterozygous. This person would be a carrier, but they would not have sickle cell disease, although there is some talk that maybe people who do carry the disease might have some traits that someone with sickle cell disease would have. Then we have someone who's homozygous, homo meaning same, recessive, because it's the lowercase s, and the phenotype for this one would be sickle cell disease or sickle cell anemia. We use those two interchangeably. It's just important that you know that having anemia is not the same thing as having sickle cell anemia. Sickle cell anemia refers to having mutated hemoglobin cells, where somebody who's anemic means that they have low red blood cell count. Okay, so some of you can just look at this and you know out of 4 how to determine the percentage, but the official formula for this would be to divide the number of boxes containing the genotype by 4, because there's 4 total boxes, and multiply by 100. So for homozygous dominant, because it's capital S, there's only one box that has that genotype. So it'd be a 1 in 4 chance. So 1 divided by 4 times 100 would be 25%. So it's 25% chance that their child would be completely normal. Next one, heterozygous. There's 2 boxes out of the 4. Okay, so 2 divided by 4. By 100, that would be a 50% chance that their child is a carrier. And little s, there's only one box that has little s, and that would mean that they have a 25% chance of passing down the disease. Okay, so we're going to now look at pedigrees and determine the chances of the children having a particular condition. So we're going to stick with sickle cell right now. Sickle cell is recessive. So remember that we have 3 possible genotypes associated with this. Okay. This person would be normal. This person would be a carrier. And this person would have sickle cell. All right. So we're using shaded squares and circles to indicate that they are affected. So that if they are affected, they have sickle cell disease. So automatically, I already know what the genotype is for parents 1 and 2. So they have a shaded square, so they would be little s, and a shaded circle, little s, little s. So they both have sickle cell disease. So when I go to do the Punnett square, and you probably already know what the probability is right now of them having sickle cell, the only allele that they can get from each parent is a little s. So if both parents have sickle cell disease, it's 100% chance that their children will have sickle cell disease. I'm going to use SCD, sickle cell disease. Okay, so in this case, that's a really easy one. It'd be 100% chance that this couple would have children with sickle cell disease. Okay. Now, in the pedigree resource sheet you received for 3.4.1, you learned that we can use a half-shaded box to indicate if somebody is heterozygous. So it might look like one of these. However, if you receive a pedigree and you don't see any half-shaded squares or circles, you need to go ahead and assume that we're not sure who is homozygous or heterozygous. So this person right here, the mom, we just need to go ahead and assume that we're not sure if she is homozygous or heterozygous. If you have a pedigree that has some half-shaded ones, then you can assume that we do have that knowledge. But most of the time, people don't know if they're homozygous or heterozygous, because you can't tell that by looking at somebody. You can only tell their phenotype. So mom can be either big S, little s, or big S, big S, because both of those would result in an unaffected parent. So she doesn't have sickle cell disease. However, the father here does have sickle cell disease. So little s, little s. And actually, why don't I use cursive? So it's a little bit easier to see which one's lowercase and which one's uppercase. So that's my lowercase. All right, so let's look at both of those probabilities. So let's do first across where we're assuming that mom is heterozygous. So the two different alleles there on the left, that's a heterozygous. If she's a carrier, what are the chances that their child will have sickle cell disease? Okay, so we have two genotypes. We have SS, which results in a 50% chance of a carrier. And we have a 50% chance that they have sickle cell disease. All right. And then the other possibility that mom can be is big S, big S. And this one is only going to result in one possible genotype, and that is that it's a 100% chance of being a carrier. So in my explanation, I would say if the mother is heterozygous, there is a 50% chance of the children having sickle cell disease. If mother is homozygous, there is a 0% chance. Hopefully you can turn on the closed captioning so you can actually understand what I'm saying there. I know that my writing is quite sloppy. Okay, so we have two different possibilities. Okay, so now we have a pedigree where we do see a half-shaded square or circle. That means that we do have the information to determine if they are heterozygous or homozygous. So in this case, we already know that dad is heterozygous, and mom has to be homozygous for the recessive trait because she is affected. She does have sickle cell disease. So when we do the cross, so they would have a 50% chance of having a child with sickle cell disease. Okay, so now what are the possible genotypes of the mother? So here we do see that we have some half-shaded squares, so we do have information about who's heterozygous. So this one is heterozygous and this one's heterozygous. Because we see that some of them are half-shaded and some are not, then you can go ahead and assume that this guy is homozygous. It's not a carrier because there is information on the pedigree that indicates who's a carrier. And then we have a daughter who's completely filled in, so she must be homozygous recessive. All right, so now we need to determine what the genotype is for the mother. So the mother can be homozygous dominant, homozygous recessive, or heterozygous. So we'll do a cross for each one of those. So let's say she's homozygous dominant. Okay, in this cross, we have two possible genotypes. We have homozygous dominant, which could give us this child, and we have heterozygous, which could give us this child. But that would not explain the daughter who has sickle cell disease. So mom cannot be homozygous dominant. Now if we do a cross where mom has sickle cell disease, again, we only have two possible genotypes. This one would explain our child with sickle cell disease, and it would explain our heterozygous child, but it does not explain our homozygous dominant, so that is not a possible genotype for mom, which leaves us with the heterozygous, but I'll go ahead and do the cross. Okay, so there we have all three of the genotypes represented. We can explain this child because of this box. We can explain this child because of these boxes. And we can explain our child with sickle cell because of this probability. Okay, now we have another pedigree where we can tell who is heterozygous. So we're going to go ahead and assume we're doing sickle cell again. Right, and we know that dad has sickle cell. So we need to determine if mom is homozygous recessive, homozygous dominant, or heterozygous. So we can already eliminate one right now. If mom also had sickle cell disease, all the children would have sickle cell disease, just like our first example. Okay, so quickly I will do a cross for homozygous dominant. Whoops. Dad had sickle cell. Okay, so if dad is homozygous dominant, it's not possible to have kids who are both, who have sickle cell disease. Okay, so this this Punnett square would not explain this child. So that's out. So that leaves us with heterozygous for the dad. We'll just do the cross to confirm. Right? There's our child with sickle cell. That explains their daughter with sickle cell. And there's a 50% chance their children could be heterozygous, so that would explain this daughter and son. And I will go over a dominant pedigree in the next video.